Welcome again, dear students. In the last class, we discussed about some examples of a vector spaces. Now, in this last section of this vector space, this class, we have to discuss some important results of a vector spaces. So, we try to prove some results. If we have a time permit, we have to also discuss some examples also. Okay, so first one is this, let V be a vector space and U be a vector, this alpha be a scalar, then alpha 0, I just differentiate these two, bold 0 and bold 0 means is this 0 is over the vector space V, additive identity of this, and ordinary 0 is the element of a field of a real number and scalar is we have to checking into this form. So because I just write the proof, I just taking V means the additive identity and 0 means the scalar is there. So we try to first prove that alpha into U is equal to 0. For this we know that for any U is the element of a vector space V, then U plus 0 of V is equal to, you have a U by this property. If we take a 0 of V plus 0 of V is also 0 of a V. So, we starting from 0 alpha times of a 0 of a V, 0 of V means this bold 0 I denoted as a 0 of V, and this can be written as a form of a alpha times of 0 of a V plus 0 of a V by the property of a addition of a vector space. And now we know that alpha times of a U plus V by the property of vector space alpha U plus alpha V. So, this can I written in the form of a alpha times 0 of a V, alpha times 0 of a V also is there by the distributive property is there. So, this means alpha of 0 of V can written in this form. Now, we have to add both side minus alpha times of a 0 V in this equation. So, we have a minus alpha times 0 V plus alpha times 0 of a V is equal to minus alpha times 0 of a V, and we have a plus, we have a alpha times 0 of a V, alpha times 0 of a V, and then because again we have to that this is we have know the property of this U plus minus U is equal to 0 of identity. So, this is nothing but equal to, you have a this give you a 0 of a V, and now because it is a vector space, this can be also associative alpha times 0 of a V plus alpha times 0 of a V plus alpha times 0 of a V, and then again this is nothing but is equal to 0 of a V. So, this is the this left hand side is nothing but is equal to a 0 of a V is equal to 0 of a V plus alpha times 0 of a V. Again using we have to this property U plus 0 of a V. So, this can be written in the form of a 0 of a V is nothing but equal to alpha of a 0. This is the required we have to prove there. So, this means we can say that in vector space V, alpha a scalar into the additive identity is given to the additive identity. Okay, now we try to prove this if we have this ordinary 0 and this is 0 of a V is also. So, we again using the real number, we know that the real number 0 plus 0 is equal to 0, and then we have to just try. So, we have to take a 0 into U can be written as a 0 plus 0 into U, and this is a real number. This can be we use the property for this alpha plus beta are the scalar into U can alpha U plus beta U. By this property we can say the alpha U plus 0 of U, and now we take this is equal to this. So, we have to adding minus times 0 of U into the both side. So, this is minus times 0 of a U, 0 of a U is equal to minus times 0 of a U plus 0 of U plus 0 of U. Now, this is again you just say that by the property of this U plus minus U is equal to 0 of a V. So, this means this is giving you a 0 of a V, and now we have to using the associativity conditions. So, this is minus 0 of u plus 0 of u plus 0 of u, and now again this is quantity is equal to you have a 0 of a v. So, by these two we can say that simply we can say that in the form of a this. So, this is left hand side is equal to 0 of a v is nothing but is equal to you have a 0 of a v plus 0 u. Now, again we have to using the property of this, we have a u plus 0 plus u is equal to u. So, this is nothing but is equal to u. So, this is 0 of a v is equal to 0 of u. This is the required result which we have to try to prove this. This is clearly we have to prove this to second result is also hold in this case. Okay, now we have to try to prove this minus 1 into u is equal to minus u, and then we can write in the form of a this we can write in the form of a this. You have to write minus 1 sorry minus 1 into u plus u can be written as a minus 1. Okay, so it's this because we have to show that this is a minus 1 to u is equal to this. So, we try to this minus 1, sorry, this I writing here. We have a minus 1 u plus u can be written as a minus u minus 1 u plus 1 into u by the property of a vectors. You can 1 into u is equal to u. We can for every u belongs to the vector space V, and this again you have to using the property of a alpha u plus beta u is equal to alpha plus beta u. So, this can be written as a minus 1 plus 1 u, and then minus 1 plus 1 you have to know that is equal to is a real number. This is 0 of u, and 0 of u know is equal to 0 of identity of a v is this thing. Okay, so this means we can write into this form. So, this means we can write minus 1 into u is equal to we have a plus u is equal to 0, and then we have to try to u plus minus u, or you can just write in the form of a this we can write in the form of a minus u plus u. So, minus u plus u can be is also 0 by the this property u plus minus u is equal to 0 of identity of a v, and now this quantity is also 0 identity, this quantity is also 0. This means we can say that minus 1 u plus u is equal to minus u plus u, and both are the same identity element. So, I just say that we have to adding minus u into the both side. So, we have to adding minus u. So, minus u plus minus 1 into u plus minus u plus, and this is equal to we have a minus u plus minus u. Now, use the associative conditions. So, we have a minus 1 u plus minus u, and then this is quantity is equal to 0 of v. So, 0 of v plus minus of a u, and this is again we have a 0 of a v. This is equal to minus 1 u plus 0 of v, 0 of v minus u, and this should be equal to you have a minus 1 u is equal to minus a u by the property we have to use in this u plus identity v of is equal to v. So, in this case we also show that this vector v is a vector space of a u, and then this condition is also hold. This is we have to show is very trivially we can say into this form. Now, last one we can say that if alpha u is equal to 0 for v, then either this alpha is equal to 0 or u is equal to 0. So, if we have a given condition is this, we have a alpha of u is equal to 0 for v, then we have to prove that either alpha is equal to 0 or u is equal to 0. So, we have to assume that alpha is not equal to 0. Now alpha is a scalar, alpha is a scalar, and this is a non-zero scalar into the suppose real number. If it is a non-zero scalar in the real number, then its inverse is also belongs to the multiplicative inverse also belongs to the this real number. Then this implies that 1 upon alpha is also belongs to the R. So this can be written in the form of a 1 upon alpha. We have to multiply it, alpha u is equal to 1 upon alpha into 0 of v. Now by this property, alpha into 0 scalar into 0 of a v is equal to v. So this quantity is nothing but is equal to 0 of a v. Now from this you know that alpha times beta of u can be written as a alpha beta of a u. By this property we have to using this associativity condition 1 upon alpha into alpha u, and this is nothing but is equal to 0 of a v. And also we know that because of the multiplicative identity 1 of alpha into alpha is giving you is equal to identity 1. So this is equal to 1 into u is equal to 0 of a v. 1 into u is nothing but is equal to you have a u, and this is equal to 0 of a v, because 1 into u is equal to always u by the property of a vector space, because this v is giving you a vector space. So when we show that when alpha is not equal to 0, then this is either giving this. Now if alpha is equal to 0, then this is a very trivial case. If we have a alpha is equal to, if alpha is equal to 0, then 0 of u, then 0 of u by the b part, we already proved that this is equal to 0. So in this case, so we have a alpha is equal to 0, we have a either alpha is, this is equal to 0 of a v. So this means is 0 of a v. So this anything we have to trivial case this is. So another way we have to just prove it to this form. So this complete the proof of this theorem. We have to prove this theorem clearly. That means if a vector space v, and we have a alpha into 0 is equal to 0 vector, and 0 vector scalar into u is equal to again the 0 vector, minus 1 into u is equal to minus u. And if we have a scalar and a vector product is equal to 0, vector and then either a scalar is equal to 0 or vector is equal to 0 is identity element of this thing. So we complete this proof. Now I just written this proof in this way. We have to adjust using axioms all this vector spaces. So what I prove this, we have to writing into this form. Similarly, for proving this, we have to using by these conditions. So that means this again we have to prove into similar way, and that's we have to also one this we have to using this equating both the part, and this part b is equal to 0, and then this also we have to explain you. This means hence this we have a result minus 1 to u. Last one we have to, this is 0, and then 0 u is equal to 0 by part we clearly result hold for 0 u is equal to 0 by part of a b part, we can just say that. Okay, now we move to the another vector space. The 0 vector is unique. That means what we have to say that in this case, this is we have a vector space. We say that this is a 0 identity element, and we say that this identity element is a unique for whole the set is there. There is no need of a any other identity element is there. We cannot say that find a 0 of v is equal to sorry, we can say that additive identity is unique, means we can say that we have a u is any vector, and then we have to additive identity is there, then is giving the u is a itself element. So this means if the u giving itself this element, means we can say that clearly this is the only one element for the whole the set is there. So now we have to try to prove this 0 vector in this vector space, and addition under additive identity 0, this should be a unique element for whole this set is there. So let us start. We have a 0 vector. So that means if 0 is a 0 vector is there, so this means we have to clearly, if we have for all u belongs to u, so u is the element of a vector space v. So we have to 0 plus u is equal to u. We have to just we have to write it. Assume that there is another element 0 vector. Suppose we have a assume w is another 0 vector in the vector space V. So this W is another vector, so this means W, sorry, we have to write this means W plus U is also giving a U. Now, because 0 plus U is giving U and W plus 0 is giving U2, this means this implies that U plus U is equal to W plus U. And now, because for all U belongs to this vector space, and then this minus is also the 0 plus U, when you can write adding this is equal to both sides from minus U is equal to W plus U, and then we have a minus U, and then be using the associativity property U plus minus U, this is nothing but is equal to 0, this is nothing but is equal to 0 by the property of this. So, this means is equal to you have a 0 is equal to you have a W. So, that means what we have to say that we say that this 0 is there, that means 0 vector is there, but W we choose another 0 vector in there, and then this W is nothing but is equal to same as a this 0 vector is the same. So, W is also the same as a 0 vector. So, this means this 0 vector in this whole set is a unique. So, we have to prove into a this form both side. We have to taking this element and this is to give these two is gives us the this thing, and then we have to by this W is equal to 0. So, W is equal to 0, which means the 0 vector is a unique vector. Now, we say that the axiom 4 is additive I inverse, means this is vector space V, and then we have a certain element into there. Suppose U is there, V is there, W is there, then we can say that the element inverse of this element U minus U is only, and then inverse of this means this inverse of a U is minus U only, there is no other element find as the inverse. That means we say that the inverse of each and every element in this set should be a unique. So, inverse of each and every element in this set is a unique, means we have to check all the element in this, and then this set is equal to unique. So, in this case we try to prove this is a unique. So, try to this we take a, suppose there exists a two different inverse element, again the same technique we take a minus U and minus W are the two different unique element of this, and then ultimately we show that minus U and minus U W are the same element is this thing. So, let us we try to this. Suppose W is also satisfy this condition. So, U plus W is equal to 0. Now, we have to record to prove that W is equal to minus U. Now, because U plus minus U is equal to, we have a 0 vector, and U plus W is also is a 0 vector. So, by these two equations we can simply say that U plus minus U is equal to, you have a this, and this we have to, these two are same. So, this is the same. Now, what we have to doing this is same U plus minus U and U plus W is there, and then we have to adding this minus U both sides. So, this is minus U, this is 0, this is 0, and this is I think is here, and this means 0 plus this is equal to minus U is equal to 0. So, then minus U is a unique element into a this set. So, this means clearly we can say that minus U plus U is equal to 0, minus U plus U is equal to 0. So, minus U is in this case is clearly is a set is a unique element in this case. Okay, so now I have to go to end. We have to try to one unusual vector space. We have to try to prove this if we have a this set R the positive is a set be the set of all positive real numbers for the vector space with respect to the following operation. Addition we define into this form, we take a product of a two real numbers, and then we have a scalar multiplication is a power of a this is scalar into this form. So, now clearly because you have a U and V are the element of a R positive, then U plus V you have to define into U into V. If we have a this is a positive real number, this is a positive real number, we multiply two positive real number is again is a positive real number. So that means we can say that we have a if we take a sum of a 2, that this means this is clearly we can say that this under vector addition is a closed. So this means 2 vectors under addition is closed. Now scalar multiplication, because you have a alpha is some real number and then u is the element of a r positive, then u to the power is a positive real number, some power is always is a positive. So this is a we have a positive real number system. We have to take a any real number. So we can, if you minus 1 upon u is again u is a positive, so 1 upon u is a positive. So this means we can say that is again, so this means u to the power alpha is also belongs to this means also close under the scalar multiplication. So now we try to prove that under these two operations this set form a vector space. So we try to solve all other properties of this. So we try to first is u plus v plus w is the same as a u plus v plus w. Now because this we start from the left side, u plus v plus w, this can be written as a u plus, then you have a vw form, and then this is nothing but is equal to again written in the form of a we have a u times vw, and then you know that u, vw all are the these are the positive real number, and positive real number under multiplication is a associative. This can be written as a uv and w, and then this is nothing but is equal to uv plus w, and uv can be written as a by the definition u plus vw. So this means we can say that this is clearly is a under addition is a associative. Now we have a u plus v is equal to uv, and because u and v are the positive real number, and positive real numbers are under multiplication is commutative, this can be written as a vu, and this is nothing relative to v plus u is there. So this clearly we have to show that this is under multiplication. So this is satisfy this thing. Now we know that there exists a element. So 1 is the element is belongs to the R positive, when 1 into u can be written as a 1 into u is equal to, sorry, we use the additive identity. So 1 is the element of this. So 1 plus u can be written as a 1 into u is equal to u. So this means 1 belongs to the R positive work as a identity elements of this, and now we have to find the u is the element of a R positive, and then 1 upon u is also the element of a R positive. So this means you can say that u plus 1 upon u can be written as a u into 1 upon u, and this is equal to 1. So this means if u is the element of a R positive, is additive inverse is 1 upon u in this case. So under addition this satisfy all the properties of this vectors space. Now we try to find the other property under the scalar multiplication. So we have a alpha plus beta u, and we have to show that alpha u plus beta u. So we have a alpha plus beta u by the property u to the power alpha plus beta. This can be written as a u to the power alpha into u to the power beta. This can be written as a by the addition property u to the power alpha plus u to the power beta, and this is nothing but is equal to alpha u, and this is equal to you have a beta. So this is also satisfied in this case. Now we have to try to prove that alpha times u plus v is equal to alpha u and alpha v. So alpha times u plus v means we have to write alpha times uv, and this is nothing but is equal to, this is alpha times uv can be written as a uv to the power alpha, and then is u to the power alpha, v to the power alpha, u to the power alpha, v to the power alpha plus by the addition property. Then we have to write this is nothing but is equal to alpha u alpha v. So this means this is clearly satisfy these conditions. Now we have alpha times beta of u alpha beta u. So, you have alpha times beta of u, alpha times u to the power beta is equal to u to the power beta to the alpha. This is u to the power beta alpha, u to the power alpha beta, u to the power alpha to the power beta, and this is nothing but is equal to, you have a beta times, you have a we have a just that we just write into the form of a this is u to the power alpha, means alpha u to the power beta, then you have a write in the form of a this is equal to, or we can just write into this form is equal to beta times of alpha u, that is beta alpha u, and satisfy all this condition into this form. Okay, so this means this satisfy in this case, and the last condition is a 1 into u is equal to u to the power 1 is equal to u, and then we have to satisfy all the properties of this into vector spaces is satisfied. So, this means we can say that in this case this all properties of a vector space is satisfied. So, we have to write this, we can write directly from here, this is alpha beta u. So, this means this whole vector space property is satisfied here. So, that means you can say that this unusual way we have to define this set under define the binary under set of a positive real number, addition is defined into this form, scalar multiplication into this form, is clearly form a vector space into this form. Okay, now I have to just conclude this lecture by this question. We have a vector space of so V is V4 means we have an element of this x1, x2, x3, x4. This is the element of a R4 such that x1, x2, x3, x4 are any real number. What is saying that he said the set of all vector this such that x4 is equal to 0, means he said that the vector space in the form x1, x2, x3 and 0. Then means he is a fixes x4 is equal to 0. Is this is a this is again is a subset of a R4 and then satisfy all these conditions. So, we have to in this case fix one element is equal to fourth element is equal to 0. So, this is under usual component by addition and multiplication is because we know that so 0, 0, 0, 0 is the element of this set, and under addition this is also closed, under scalar multiplication is also closed because it is a subset to satisfy all these things. So, this answer is a yes, this is a this thing. Now, we have a fixing is this we have a V is choosing into this form, we have a 1 x2, x3, x4, then x2, x3, x4 are the element of a R. Then clearly 0, 0, 0, 0 does not belongs to V. This additive identity is not here. So, this means we clearly say that this set is not from a vector space. This is clearly answer is equal to no. If we take a strictly greater than 0, then again in this case you see 0, 0, 0 and 0 is does not belongs to the set vector space, and also we have a if you have a 1, 2, 3, 4, then you have a minus if you take alpha u, if alpha is equal to -1, so we can say that is equal to 1, -1, -2, -3, -4, and this is -2 is not greater than 0. So, even this is not a identity element is not there, and also under scalar multiplication is not closed. So, this is clearly is not a vector space in this case also, this is no. X3 is greater than equal to 0 is again is answer is a no. Why? Because is 0, 0 is clearly belongs to the this set V, but alpha u does not belongs to the V, because this x3 you have to take as 0, 1, 5, 3, that is clearly belongs to the vector space, we have to greater than equal to 0. Now, alpha is equal to I take a suppose is equal to -1. So, this is alpha u is the form of a -1 to 0, 0, -1, -5, -3, and this we have x3 should be greater -3 -5. This is element is we can say that this -5 is not greater than equal to 0. So, this is not a clause under the addition under this vector space. So, I just say that this all the these things. So, now I have to conclude this. This is some home assignment for you. This you have to working. We have to define some additions of uh, vectors in this R2 we take addition is defined to this form and scalar multiplication is defined to this form. Now they show that this form is a vector space, compute additive identity and additive inverse for this, and this is the last question. So, we have to define addition and scalar multiplication of polynomials into this form. So, compute the 0 vector of this and also compute the identity additive inverse or prove or disprove that V is a vector space, define the addition and scalar multiplication or not. So, thank you very much. In the next class, we introduce the concept of a subspaces. Thank you.